All right, so for part 2 of this one, we're going to talk about the mechanisms of reactions and how they work. So temperature, as we said earlier, as temperature increases, so does the reaction rate, because that K is temperature dependent. So anytime you have a K, again, it's based on a specific temperature. So if you calculate it for 100 degrees Celsius and you change your temperature to 50 degrees Celsius, you need a whole new K. So in a chemical reaction, bonds are broken, new bonds are formed, obviously, and molecules can only react if they collide with each other, and they have to collide with each other in just the right orientation and with enough energy. Right? Otherwise, you have to be able to make the bonds break, and you have to be in the right spot for new bonds to form. So example down here, these are your molecules before your collision. These guys collide, and they're going to form a Cl2, and this is your leftover stuff. But if this molecule, you can see, is rotated here, they come in and they collide like this, obviously you're not going to get a Cl2 molecule from this collision. Boing, just bounces off and no reaction happens. So that's why the more you're in motion, the more likely you are to A, run into something else, and then B, run into something else with the same orientation. And then if your temperature is higher, you're going to have more energy, and you're more likely to have enough energy to cause that bonds to break and new bonds to form. And so we call that the activation energy. So there's a minimum amount of energy that you need to make a reaction happen, right? So their analogy here is the golfer here. If he only gives a soft putt, the ball might not make it over. He has to give it at least enough energy to get the ball over the hump, and then he can get down to the pin. This is the energy basically that you need to stretch, bend, and then ultimately break the bonds so that you can form some new bonds. And we can use something called the reaction coordinate diagram to visualize this process. So if we're sort of thinking of these things in like a Lewis structure here, these are the bonds that we're working on. As you increase your energy, we can see what's going on with the products. So as we increase energy, we see that this molecule is starting to bend here. At the high point, you've given it enough energy to break that bond. Right? This is called the transition state. This is where something called the activated complex forms, where these guys are ready to react with something new or react with themselves in a different way. And then now we're no longer putting in energy. Now, hopefully, we're getting energy out. And so the activated complex is free. It's crossed that activation barrier, and now it's a downhill shot for this to turn around, for this C to bond with this C now. And so down here end up with a net gain in energy. You're putting in energy going up and then coming out with energy. You get a net gain. Endo versus exothermic, we've used those terms before. If it's an exothermic, the products are going to be more stable than the reactants, so heat is going to be released. Heat exits the reaction. If it's endothermic, it's the opposite. So endothermic, heat gets absorbed, so our product has heat's being absorbed. It's not giving us energy back. These guys are going to be less stable in this case. So in this example, we're asked to rank these reactions according to their rate. Which one's going to be going the fastest and which one's going to be going to the slowest. Well, if we look at this one, number 2, this one has the highest activation energy. You have to put the most energy into it. So this one is probably going to be our slowest. So this one will be the bottom one. If we look at these two, we're looking at a delta E of 25, right? 28 to 5 and 15 to negative 10. So in that aspect, they're equal. However, this one here is exothermic, and this one here is endothermic. So then that means that of these guys, which one's going to be going slower? Well, the endothermic reaction is going to go slower than the exothermic reaction. So reaction 2 is less than reaction 3, which is less than reaction 1. Reaction 1 is the fastest. Reaction number 2 is the slowest. Okay, moving on to reaction mechanisms. Reaction mechanisms is just what this says, is the sequence that actually happens to produce the reactant. So you might have some intermediate processes that aren't actually shown in your overall equation. So they might occur through several steps, or they might occur all at once. And so if it does occur over multiple steps, each one is known as an elementary reaction or an elementary process. And so we often talk about these in terms of molecularity. And so the molecularity of a process tells us how many molecules are involved. So something like this, one molecule is involved as unimolecular. by the way, we're talking only the reactants, right? This guy would be bimolecular. You've got two of the same thing. This one has an A and a B, two different things, but still two, so it's bimolecular. And then you can have different combinations of termolecular. So in this case, for elementary steps, now the rate laws are based on their molecularity because we know this is what's going on. Right before, we couldn't use molecularity, we couldn't use our stoichiometric ratios because we didn't know if there was a intermediate step or whatnot. But since we're using these as our intermediate steps, we can use those to figure out what's going on with the rate laws. So if it's unimolecular, it's a first order, right? And the rate is going to be this. If it's bimolecular, it's going to be a second order reaction, and the rate is either going to be Ka squared or Kab. If it's termolecular, you really don't need to worry about it. They're very rare. It's beyond the scope of this class. It's very rare because if you think about it, you have to have 3 molecules colliding in the proper orientation with enough energy regularly for the reaction to happen. So you can see that's not going to happen all that often. When you're talking about multi-step reactions, one of the steps is invariably going to be slower than the others. And this is what's going to determine how fast that reaction is going to go overall. We're going to call it the rate determining step. So like in this diagram here, all the cars are bunching up at Toll Plaza A, but don't seem to be having too much trouble getting through Toll Plaza B. So we say that this is the rate limiting step, the rate limiting toll gate. Versus in this diagram, they're zipping right through Toll Pass A. They all have easy pass. They're flying through. But something's wrong with the easy pass lane over here, so they're bunching up. This is what's going to be dictating the speed of traffic. So in this case, this guy is the rate limiting step. So if we have a slow initial step, that makes things a little bit easier. So if we look at this reaction here, NO2 plus CO yields NO plus CO2. The rate law for this guy experimentally we figured out is K NO2 squared. So does that really make sense with what you see here? No. If you were just to look at that, you wouldn't write this rate law. So that tells us that something is happening, right? CO is probably necessary for this reaction to occur, but the rate doesn't depend on it. Otherwise, it would be in our rate law. So it's not showing up there. So this suggests to us that this reaction is occurring in different steps. Something is happening that's not being expressed in the rate law. It's something's happening that's not governing the speed of this reaction. So a proposed mechanism might be for this. In step 1, you could have two different NO2 molecules combining to get NO3 and NO, this being our slow step. And then this guy, this NO3, would combine with the carbon monoxide to get your NO2 plus your CO2. In this case, we would say that NO3 is an intermediate, right, because it's only showing up in the middle, and it gets totally consumed. That's why it's not showing up in any of your products. And it's not involved in the slower step, so it's not going to appear in the rate law. And this slow step does jive exactly with what the experimental rate law was, which was K, the concentration of NO2 squared. So put this into an example. We've got this reaction here, ozone reacting with nitrogen dioxide. And so we think it's going to happen in 2 steps. These are our 2 steps. And so these are our questions. Why do we think, what makes us think this is a 2-step reaction? What's wrong with just writing out this way? Well, what did I say about molecularity? This is a termolecular reaction, 1, 2, 3, and those are pretty rare. So we wouldn't expect that to be the case. And then the second part of this is the experimental rate law is K, concentration of O3, concentration of NO2. What does this tell us about the relative rates? Well, what does this match up with? This matches up with our first step, not our second step. So since it matches up with this, that's the one this is the rate law. That means the rate is based on this step. So this must be your slow step. The step 1 is your slow step. This is your fast step. But what if we have a fast initial step? Then it gets a little bit trickier. So if we're looking at this reaction here, 2NO plus Br2 equals 2NOBr. The rate law for this reaction experimentally is found to be K NO squared Br2. NO squared Br2, okay, that doesn't seem to make sense. Because it's a termolecular process, right, it's probably not that. It suggests that it's a 2-step mechanism. So one proposed mechanism is this. Step 1 and step 2, we think the step 1 is a fast step 2 is a slow step. And notice that for step 1, we've got forward and reverse arrows here. That's going to become important. So the overall reaction depends on the rate of the slow step, like we said, which was step number 2. So the rate law for that step would be K sub 2 NOBr2, concentration NOBr2 NO. But how do we find this concentration? Right? We're not given that. That's just an intermediate that totally gets consumed. So is that helpful? Well, it turns out yes. So if we think about it, NOBr2 can react in two different ways. It can react with the NO to form the NOBr, which is what we saw in the rate steps, or it can also decompose and reform back to NO. And so the reactants and the products of the first step are basically in equilibrium with each other because that's the slow step. And so they're piling up there at that toll plaza. So as some get formed, some are also going to decompose and go back the other way. And so we can say that the forward rate equals the reverse rate in that slow step because it's being held up by that second step. So because of that, we can rewrite our rate expression like this. So K sub 1 NOBr2, which is what it was in the overall reaction, and then it equals the reverse of that. So if we solve for concentration of NOBr2, this is what we get. So now that we have a new way of expressing our concentration of NOBr2, we can plug that into its spot in our slow step, so right here. And so that gives us the rate equals, this is our expression for NOBr2 plus in your NO. So that's our rate law there. And simplify this into K NO squared Br2, which is what we had experimentally determined. Finally, talk a little bit about catalysts. These are the last things we said that can change the rate of a reaction. So they can increase the rate of a reaction by basically they decrease the activation energy. They do something that makes it easier for the reactants to come together. They lower the energy somehow, so it's easier to get over that hump. They change the mechanism by which that process occurs. So one example is they sort of hold those reactants together and help break the bonds. So this is a catalytic converter, I think is going on in here. So the carbon gets held on by this catalyst, and then you can add these hydrogens to the molecule, and we've changed that substance, right? So it's about making that reaction happen faster. And like I said earlier, we have probably heard of them more in the context of biology. And enzymes are catalysts in the body, and basically if this is your enzyme, it gives a spot for the substrate, whatever it wants to change, to lock in there, and then it can help those products be formed. It's like a lock and a key, so every enzyme in your body works with a specific substrate. And that is the end of kinetics.